Good afternoon, everyone. Today I'm going to talk about scaling training of large language models to hundred thousands of GPUs, and challenges we encountered at Meta while doing so, and solutions we explored. My name is Saif, and I am a software engineer at Meta. Before we delve into the details of exciting part, let's briefly take a look at the evolution of LLMs. Across the industry, they are evolving at an unprecedented scale. And with every generation, the model is getting bigger. At the same time, it's also getting trained on larger amount of data. To do so, we need large amount of resources / GPUs. Llama 2 had 70 billion parameters trained on 2,000 GPUs. With Llama 3, 450 billion parameters trained on 16,000 GPUs. And Llama 4 with 2 trillion total parameters with 288 active parameters to be trained on 100,000 GPU cluster. So the typical training life cycle of this LLM lasts for several months. And they do so in an increment of small steps, which is often takes a long time to conclude. Now, during this whole training phase, there could be intermittent failures, often from the hardware components involved into the training. So whenever there is a failure, the job has to be interrupted, and it has to restart. And it does so by leveraging the most recent checkpoint that it produces along the way. So as we noticed, the job is started many, many times during the lifespan of its training. Now, the key thing, whenever a job starts, the scheduler first has to allocate all the resources, load up your binary, and then starts the processes. The first thing that happens as soon as process starts is the initialization phase, in which I'm oversimplifying it, but the key three components over here is collective initialization, that is providing an ability to communicate across all the GPUs and loading the model, as well as prefetching some of the data that needs to be trained. Once the initialization is complete, the training loop succeeds afterwards. The thing is, as we scale the job, the collective initialization increases with time because it's directly correlated with number of GPUs involved in the training process. However, model loading and the data checking more or less remain static with respect to the size of the model and data involved in there. As we can see in this diagram, we observed that at 4K scale, collective initialization to be taking only 112 seconds alone. At 96K scale, we anticipated to be taking 15 minutes of time just right there for the collective initialization. So as we scale the job, the number of hardware component increases. That means the failure rate associated also increases. We anticipated one failure every 30 minutes to be at full 96K scale. And at the same time, initialization time also increases. So you initialize your job for 15 minutes and try to train before within a 30 minute you encounter a failure, and then go about initializing again. This means your effective training time is 50%. So for the 50% of the time, your GPUs are not computing anything at all while they are trying to initialize. At the same time, you waste a lot of GPU hours, but your training time is also requires more time to conclude because your GPUs are sitting idle more of the time. So our goal here is to optimize the effective training time of the job. We explored two solutions. Number one is to improve the initialization time of the job by directly improving the collective initialization, which has been the biggest contributor. And the second one is a fault-tolerant paradigm, a training paradigm that enables us to isolate the fault to a subset of GPUs and enable us to train with the remaining healthy GPUs that are part of the job resources. So let's take a look at the collective initialization and few of the notable improvements that we did here at Meta. Collective initialization often requires creating multiple communicator, which is an abstraction over the communication patterns that GPU requires, all gather, reduce, scatter, all to all, right? And there is one global communicator created that encompasses all the ranks that are part of the job. And there are multiple sub-communicators created, often mapping to each of the parallelism there. Whenever a communicator is initialized, it goes through 3 key phases. First, it goes through a bootstrap phase, in which it has to discover the ranks or GPUs that are participating in the training. They do so. So once they discover their peers, they'll connect to them. And then when everyone connects, they form the ring. And they use this ring in order to exchange the data among all the GPUs involved, which is all-gather phase, to exchange the metadata. Once the data is exchanged, every GPU has a view of all the participating GPUs in the communicator. In the communicator. So they do topology computation. They find the paths on which the data needs to be shuffled subsequently. And then they set up the data channels afterwards. So one of the key notable improvement was in the bootstrap phase, because that's directly correlated with the communications among the GPUs, while the other two are more related towards the local computation within the process itself. The key notable improvement was in the ring formation itself. The default implementation is root-based initialization, was estimated to be taking over 2 minutes alone at 96K scale. So we improved it with TCP store-based initialization, which is a simple key value store in which a rank will set its address and will get the addresses of the peer and connects to them. This is not something that we implemented, but rather already part of a training stack for all the training models which are using PyTorch. And it is an asynchronous by design and multi-threaded. So this simple distributed optimizations of handling parallel connections and doing asynchronous I/O provided us an optimization that at 96K scale, it just requires 10 seconds to form the ring, while the default implementation was taking around 132 seconds. So 2 minutes of time saving right over here. The second notable piece is in all-gathers, which we described is the mechanism of exchanging the data between the GPUs during the initialization phase. This is all-gather is performed several times, and thus is one of the key contributors taking much of the time during the initialization. The all-gather is performed in a ring fashion where a peer will send its data piece to the next guy and receives the data piece from the previous. And it requires n-1 steps to conclude so that everyone has all the data pieces. We did a very simple implementation, optimization on top of it, which probably, as you can see from this diagram, is to do it both directions rather than doing only in the forward direction. So in that way, you need only n/2 steps to conclude. And this cuts down the all-gather time or the bootstrap phase by half, and it's a notable improvement at a large scale. Now, you may ask, is like why we are able to do so, but not like we don't do such bidirectional ring for the collectives that are implemented down in GPUs. One of the key things to note here is that we are only exchanging metadata in not large amount of like memories during the bootstrap phase. So we are not bandwidth bounded as such. So we are not bandwidth bounded. So most of the time, we are just waiting for the data to arrive and not saturating the NIC at all. So thus, this optimization played a role, like a notable role in improving the initialization time. So we did these optimizations, and we did few more. It would be too much to maybe like include all of them in here, but we were very proud of all the stuff that we did, and we did an 8K run on 8K GPU cluster, and we saw some notable improvements as well. However, we did not have more resources to do a further large-scale initialization runs. But we wanted to be ready whenever the GPU resources land, right? So what we did was we had a lack of GPU resources, right? And how do we overcome that? So we thought of taking a collective application which runs on a GPU and run it on a CPU. In order to do so, we needed to solve two key problems. the application that runs, the collective application that runs on a GPU has two key hardware dependencies. One for the CUDA, in order to program the GPUs for the collective kernels, and then the another is the IB verbs, which is to program the NIC for RDMA instructions. And we mocked both of these implementations. With this, we took the collective library, collective application, and compiled it over for the CPU, and we're able to run it without any single line of modification in the application. Now, this doesn't enable us to run the GPU components of it, but for the initialization piece that we were concerned of, we were able to try out the full, complete execution of the whole initialization process. On the top of it, we packed 32 processes on one CPU node, usually 8 processes per GPU node. So we thought, let's give it a try and see if it goes through or not. And there were a lot of surprises to us when we tried running. The first thing, whenever we are running a job, we saw there was a very high utilization for a sustained duration of time. And it was not just concluding to initialize. So we were like, how to solve the problem? That's when the CPU profiling tools came in very handy. We just run the CPU profiling tool. It spotted us that, hey, these two pieces of your function in your code is taking most of the time over there. And once we spotted those things, as you can see in here, it was just order of n squared, with n being 100K, 10⁵, just like several tens of billions of operations right over there, which will consume dozens of CPU cycles there. The second notable key thing was that the TCP store optimization that I described, every rank connects to it. So as you scale, the number of connections TCP store needs to handle grows. And beyond 64K scale, we started seeing connection errors. And once we spotted the error, it was very obvious that, yes, there is a listen queue overflow settings in the system, which was already set to 64K, pretty high number. And because of that, there were silent connection errors. In both of these cases, finding the problem was very hard. But once we knew where the problem is, solving them was super simple. And we were able to verify that, oh, once we solve this, we are able to initialize successfully. On top of it, we had some more ideas to optimize even further. Like altogether, I described the optimization. You would have probably think that, oh, you are just trying to optimize from n to n by 2, but you are not changing really the complexity of it. Tree can probably give you a logarithmic complexity. We thought of the same thing to do, and we implemented a tree-based altogether and tried it out on our emulation platform. And we learned that at a large scale, it's not giving any performance improvement at all over the ring-based implementation. Now, it seems contradictory, and we were also kind of surprised by that result. And when we digged in deeper, we learned that that's because for a tree, the traffic funnels to the root node. And for every packet, there are small messages. And for every packet, you have to do send and receive calls, and which goes through the Linux kernel networking stack. And those were the biggest contributor in terms of slowing down the overall completion time. So what we did is we ruled out the tree in favor of ring over there. So optimizing collective initialization helped us get better effective training time. Let us shed some light on an alternative approach of fault-tolerant training. So a large job problem is that whenever there is one single failure, we kind of lose all the GPUs that are part of the training job. The thesis of fault-tolerant training lies on isolating a failure to a subset of resources and enabling the other resources to continue training. So before we dig in deeper details of what the fault-tolerant training looks like, let us understand the parallelism aspects. So a model cannot fit on one GPU, so it needs to be sharded across the GPUs, and it often follows a simple 3D parallel strategy, like you do PP splits and TP split and use FSTP, and which through which you completely like shard your model parameters across all the GPUs that are part of the training job. Now, even if you lose one single GPU, you lose some part of your model. So you don't have the full model in order to run a step. So while we're training big models, the model is not big enough, like 2 trillion model, that you need 100,000 GPUs to fit that. It often can be fit into 4K to 8K GPUs alone. So we use like replication model, where we have each replica is containing the full model, and then we kind of scale up the data parallel dimension so that you can train on the data in parallel, and use all reduce to synchronize your gradient at the end of the step. This is not a new parallelism as per se. The people in the room familiar with it would notice this is called HSTP, hybrid sharded data parallel, and PyTorch provides an implementation of it. The key difference, however, is that what if we can try to bring down the replica while allowing the other replicas to continue training? However, in order to do so, what we need is the all reduce, that collective that goes across the replica has to be fault tolerant. So we model our job as multiple task groups, and each task group representing one replica in which the model is fully sharded. And model architecture and required performance would determine what is the size of the replica and how many replicas we have. And we synchronize the gradient using the fault-tolerant all reduce. This is still a full sync training because at the end of the step, you synchronize all the gradients. Now the key notable difference here is this fault-tolerant, which can like absorb a loss of a replica. In order to build fault-tolerant collective, we needed to build a system around it. The one key notable thing is to build a coordinator that sits outside of the job into which all the replicas checks themselves into. So replica says, I'm alive, and then replicant can request, give me the set of alive replicas. We call it as a quorum view. This quorum view is then used to create the communicator and then resize it as the quorum expands and shrinks and grows. So whenever there is a loss, like whenever there is a fault in one of the replica, only that replica goes down. When it goes down, the shrink phase happens. On the healthy replicas, you will notice that the enqueued collective will time out because there has been a fault for the collective that is going across all the replicas. And this is bounded by a timeout value. Subsequently, all the replicas will check themselves into quorum and get a new quorum view in which they notice that it has shrink by 1. And then they'll form a new communicator with n-1 participating replicas, and then they'll go about retrying the steps that failed and resume the training. Then once the replica that was down, it will take its own time to come back up, initialize, and request to join the quorum. At which point, all the replicas that were training already, they will stop. They'll allow the new replica to join in. The key thing here is that the new replica needs like a model state and the data. So it gets the data from its most recent checkpoint that it failed at. And it gets the model state from the healthy replica that were training while it was down. Once this is retrieved, all the replicas will start performing the training steps again. So as you can see in this diagram, during the shrink and the grow phase, the training halts, so all the GPUs are idle. But we were able to contain those two phases within 3 to 4 minutes of time. So this improves our effective training time significantly. So to recap, both of the approaches that we discussed, one is like collective initialization, improving the collective initialization time, and fault-tolerant training enables us to achieve an effective training time of up to 90%, up from 50%, which was our expectation. Collective initialization directly improves the time, while fault-tolerant is a different paradigm which allows you to reuse your healthy resources while the bad resources recovers. So to recap, some of the key learnings from the talk is as we scale the training, the hardware failures are inevitable and they become very frequent. And every time there is a failure, the severity is very high. Recovering faster is the key to use the GPU resources effectively. A novel approaches such as emulated frameworks was key to overcome GPU resource limitation and gain confidence and iterate rapidly for the solutions, for the optimization solutions. The collective initialization improvements that I described about are upstreamed to the nickel and should be available for wider community to benefit from. And fault-tolerant training paradigm has proved to be practical, and sometimes we have to go to rethink the approach, the way we do training. Though we took big leaps in training, scaling the training, we still have a long way to go. As you would have seen, like Guy talking in the keynote earlier today, like we are building even larger clusters up to 1 million GPUs. For Llama 3, we thought we were done for life at 16K GPUs and we would not need more GPUs to train future LLMs, but we are completely wrong with Llama 4 and even again wrong with like with million plus GPU cluster. The fault-tolerant training is an emerging paradigm and its associated collectives are also evolving rapidly. There are many things that are open here. So with this, I'll conclude my talk. Thank you all for listening, and bring on your questions for the following Q&A session.